Okay, I think I messed up with one of my cameras, and I'm doing that way too often. And with at least one of them, I didn't get the first part of this. I think I got it with one of the cameras. I think I turned the camera off when I thought I'd turned it on when I thought I'd turned it off, because I caught myself writing a bunch of new stuff with the camera on me without saying anything. Okay, well, that's all as it is, but what we want to talk about is vertical shifting. So what we did was we started here with the graph of y equals x to the p. So that's our f of x function. That's the white function here. And then we displace each y value by this arrow to get our g of x function. So we take, we have this point, this point, this point, this point, and this point, the points I used to construct this graph. I'm going to take each of those points and apply the vertical arrow. So I apply it here, takes me to a point here. I apply the same arrow here, takes me to the point here. I apply the same arrow here, and it takes me up to here, and this point goes to here, and this point goes to here. So that I get this graph here that has exactly the same shape as this graph, but it's this much higher. Okay, so that differs from the vertical stretch, because remember, for the vertical stretch, the graphs kept getting further apart. Now, I use that term further apart a little bit loosely, because clearly these graphs are also getting further apart. So what I want to clarify is that by further apart, I mean that this graph will be higher than this graph, always by the same amount. So the vertical distance between the graphs, the vertical distance you have to travel to get from this graph to this graph, is always the same. Now, of course, the graphs do get closer, well, further apart as you move away, but the vertical distances remain the same. So, and we pose the question, what's the equation for the g of x function? Okay, because this green function is going to be our g of x function if the vertical displacement is represented by the letter k. We don't have a scale on this graph, and I don't want to put a scale on this graph at this point. We want to do this purely geometrically. We don't want to have to worry about a bunch of numbers. All I'm saying is that we move each point some distance higher. And it might be a greater or a lesser distance. It might even be a vertical displacement in the downward direction, in which case your vertical displacement would be represented by a negative number. Whatever the number is, whatever the scale is. So, if this represents our vertical displacement k, what's the equation for g of x? Okay? Now, another question. First of all, g of x is what we're going to call a generalized power function. Okay, I've already kind of given you the form of a generalized power function, not that I expect you to necessarily remember it, but it was given in some of the introductory videos. My question is g of x a power function? Now, what do I mean by a power function? By power function, I mean a function of the form y equals x to the p. Okay? That's what a power function is. A generalized power function has some extra stuff, but a power function is y equals x to the p, or a vertical stretch or a multiple of a y equals x to the p. So it's a y equals a times x to the p. Anything else is not a power function. And as we've seen, the power functions have the geometrical characterization that doubling x always changes y by the same factor. So you have a geometric test, and there's also an algebraic test. But I want you to really think about the geometric test right now, because we haven't gone deeply into the algebra of power and exponential functions. So geometrically, can you show whether g of x is or is not a power function? If you can do it algebraically, great, but you're probably not at this stage in a position where you can really handle that question. If you are, then you're doing extraordinarily well. Very unusual that anybody would be able to handle that. without a little guidance, and we'll get some of that guidance later. Then the question is, remember this means there exists, and with a question mark it means does there exist a displacement k such that g of x is a power function? Is there some k not equal to 0? Because of course if k equals 0, you haven't changed the function, so it's still a power function, okay? But if k is not equal to 0, does there exist any non-zero k for which this g of x, excuse me, something's blooming, I don't know, for which this g of x would be a power function? Now, if your answer here is that g of x is a power function, then presumably it could be a power function for every value of k, in which case there certainly would exist at least one k for which it is, and your answer to this question would be, duh, yes. Okay? The other alternative is you prove that g of x is not always a power function. Can it sometimes be a power function for a non-zero k? All right, well that's the content of the first part of this video. In the second part we go through and ask some questions about exponential functions with a vertical displacement, vertical shift, and also a question about an exponential function with a vertical stretch. So we'll come up to that in a minute.